Hello and welcome everyone to this virtual meetup titled Exploring the Capabilities of H2O-3, the #1 open source machine learning platform. My name is Ivan Trehin and I am on the marketing team here at H2O.ai. I would love to start off by introducing our speaker today. Stefan Pachinda is Solution Architect at H2O.ai. Before I hand it over to Stefan, I would like to go over the following housekeeping items. If you have any questions, please type them into the Q&A box and we will answer them at the end of the session. And this session today is being recorded. A copy of the recording will be available after the presentation is over. Now I would like to hand it over to Stefan.
Hello everybody, thanks Ivan for a nice introduction. So the topic of today's webinar will be looking at H2O's open source platform, which we call H2O-3, and try to explore what we can do and how it can be beneficial for machine learning. So first things first, what is H2O as a company? It's a startup based in or HQ'd in Silicon Valley in Mountain View, founded in 2012. It's already well funded by some leading investors. The platform, the H2O platform, comprises of several offerings. The H2O-3, the open source machine learning platform, which is the original piece of software that H2O started with. H2O driverless AI, which is automatic machine learning platform. H2O-Q, platform for business users that provides vertical solutions, and ModelOps, which is enterprise-grade platform for managing your machine learning models. We do have global presence on most of the continents. HQ is in Mountain View. We have large office in Prague, London, Paris, and other places. The presence of H2O tools on the market and among the data science community is really large. Our tools are being used by thousands of data scientists, leading universities. We are very active in Meetup community, and hopefully this is not the first time you hear about H2O, and more importantly, not the last time. So coming back to the platform again, the first piece, and the piece that we will be interested in throughout the rest of the session, is our distributed machine learning platform and its version that is ported onto Spark, which is called Sparkling Water. So these two are the same two things on different platforms. Then driverless AI, which automates some of the steps that we will be trying to do manually today, and H2O-Q. So, and then we do have underlying deployment and management platforms. So I will briefly touch Enterprise Team, which allows you to deploy your clusters of your H2O-3 platform on various underlying technologies like Hadoop, Spark, or others. Then Enterprise Puddle, which is sort of the same thing, which mainly focuses on deployments onto cloud providers, and the H2O ModelOps, which is a platform where you would deploy your models, monitor them, and make sure that everything works well in production. So H2O-3, let me just start with why do we call it H2O-3? It's the third major version of our open source platform, and it has been called H2O-3 for a couple of years already. So it is foremost a machine learning platform. It's fully open sourced, in-memory AI engine. The key thing about it is that it can build models and run algorithms in fully parallelized and distributed fashion. Some of the algos that would be interesting for us are generalized linear models, random forest, gradient boosting machines, and some deep learning algos. From a infrastructure point of view, this platform is super easy to use. The deployment or installation is pretty much equals to downloading your jar files and just instantiating them anywhere you like. It's written in distributed Java, very well optimized for performance. It can be accessed from a number of different clients. We will look at that in a bit. And what's the most important thing to keep in mind? H2O-3 is a big data enabled machine learning platform. So you might face this this sort of a question: do I need more data or better models? So the aim of H2O-3 is to allow you to build really good models on all of your data that you have at hand, and therefore achieve the best possible accuracy of your models. H2O-3 offers two classes of machine learning algorithms, supervised and unsupervised learning algos. When it comes to types of algos in general, we do have statistical models, ensemble models, mainly tree-based models, and some deep neural nets, and clustering algos. Algos that help you build more usable data sets by dimension reduction, some NLP algos like word embeddings, time series specific stuff, and also modules that help you with hyperparameter search, list stopping, and all of that can be applied together with the before mentioned algos. What's the latest addition? In case you have already followed H2O-3, we've improved AutoML significantly. We've added new portions for CoxPH algos, have distributed XGBoost, support for multi-node clusters, and have done some minor improvements in some of the algos. Let's have a look at the overall picture. This should hopefully put the whole process into perspective. So you would as every data scientist, you start with data acquisition. You can load your data from a number of sources. We have native connectors to many data sources, and then you would utilize the platform, and within the platform already you would be able to parse the data, do some exploratory analysis, feature engineering, train your ML algos, then have a look at the model, assess the model quality, and then use it for scoring, and potentially export the model into some of the production environment that could be anything that can run Java really, and namely some of the interesting ones, anything that really to embed within Java code, Hive, Kafka Storm, Spark, and many more. The whole platform can run typically on Hadoop or Spark, and we also have a new addition that allows us to run on Kubernetes. And then there are clients that I will just explain in a little bit. So how does the whole thing work? This is a single machine, and it stores your data in a tabular form, which is this blue table here in your main memory. And you would build your model, use some CPU operations, and this would be your H2O cluster of one node. Well, there's not much use when you can fit it in memory. You might not need to use H2O even. So you scale out. So the same thing that I showed on the previous slide, you would have running on a number of machines that are interconnected, and H2O is offering you to use a distributed key value store behind the scenes that that enables the all the distributed computations. And this is all being hosted on most likely on your Hadoop, or using Yarn as a scheduler, or Spark, as I've said. Now, from a client perspective, from a data scientist perspective, you have your H2O cluster as one homogeneous thing running somewhere in your data center. And then you have your, so in this instance, this is RStudio. So you as a data scientist would be writing your code as you typically do, with a bunch of libraries. And then at a certain point in time, you wanna read a really large data set. So you would call the H2O get frame, and then your cluster initiated on several Java virtual machines out there in a cluster. You would communicate to it through the REST API. On each of those nodes, there would be a portion of your data set, portion of each column. So the representation is really columnar one with a lot of optimization and compression. So this kind of shows you how your data set that comprises of x1 to xp columns for your predictors, and the y column for your target, would be distributed across the cluster. And you as a data scientist only communicate through the REST API, which is hidden for you behind the scenes, and never gets this whole massive data set that would never fit on your laptop, which you are using onto your computer. Now, the user interfaces are the most useful ones are three. So it's Python, and in this case, I'm showing here Python Jupyter Notebook. Or you could use RStudio, or something that we call H2O Flow, which is our homegrown nice point and click interface, which I will be showing as well. So I'm a more Python oriented person, so this time around I'm sorry to not to show any R code, but everything that I will be doing in Python can be done and achieved in R. So we will jump right into the live demonstration. So I have provisioned myself a machine on EC2 that hosts my Jupyter Notebook, and that will also be hosting my my one node H2O-3 cluster. So this is an outline of what we will be doing. So I will talk a little bit about the data sets, set up our data, do some splitting and a couple of preliminary tasks to prepare, and then we will be working with three different algorithms today. That would be GLM, random forest, and a GBM. So we'll try to build a model with each of these three algorithms, and we will do that from Python, from this Jupyter Notebook, and then also from the H2O Flow, which is the point and click interface, and we will compare how both ways are looking, and what is it. And you may find one or the other more useful for yourself. In the later stage, we will go ahead and do something more advanced, and we will revisit our trials with those three algorithms and try to improve the performance of the model by optimizing the hyperparameters of the models. So for those of you that might be new to machine learning, each of the models has a set of parameters that you can change, and then based on the data, it may come up with a better model, because you may allow it to dig a little deeper in one or other direction and find some useful data. Lastly, in the task 10, we will compare the performance that we have reached throughout these experiments. And I have on purpose used our training examples. So for those of you who would like to try out some of the stuff that I would be doing here, you can visit our training site, training.h2o.ai, and try that for yourself. It's nicely documented. So for the sake of reproducibility, I'm going to be working with this data set. So without further ado, I will go into the initial setup. Or perhaps, Ivan, if we have any questions, that would be good to ask at this point. It's also possible.
Yes, let me take a look at the questions.
So anything that is high level and not code related. So.
Okay, then I'll keep the code related questions for the end. Thanks. I think you can go ahead.
Brilliant. Okay, good. So in the initial setup, we will do we will import some of the libraries. So this is actually the only library that is H2O related. You can get that from our website. You can pip install it. We do have it on PyPy, and you can get it in many ways. You can also get it from Maven coordinates and other places. So this is fairly easy to install. I already have all the dependencies installed here. So let me just run it, and for some reason, yeah, let me just reload this because it is hiding bits of the text. Let me just reload this. Okay, it's much better now. My kernel is working, so let me just redo this. So basically, I'm just loading the GLM, GBM, and forest and grid search that we have discussed. You can see that this comes from the Aquarium platform. So I already have my datasets in place and such. This is only for this allows the script to run also locally. So I won't bother with it. And the magic comes to happen now. So I'm running H2O init with the local URL, and this will do one of the two things. It will just have a look whether there is a server running at that particular URL or not, and if not, it will instantiate that server. So the server is now up and running, and I have some information about the cluster here. So you can see that I actually already have started it when I was preparing for this. The cluster version 3.30. The cluster version H is 1 month. So this is the I think the last stable release, and I can see the total number of nodes is 1. I have 13 gigabytes of memory, so this is really small cluster. 16 cores at hand, and some more things like algos, extension algos, and etc. And you can see that from now on, whenever I will communicate with the cluster, I will use this proxy object H2O. So whenever I call H2O, I will not be doing stuff locally on my machine, but I will go ahead and through the REST API, I will call the remote cluster. You can just ignore the fact that the remote cluster is just running in a different process on the same machine, but that would not be your production environment, right? So first things that I want to do is read the data set. So I'm reading the data set through my H2O proxy, and I'm reading it from AWS, from S3 bucket, and I can see that it's being parsed now. So
Hey, Stefan, just real quick, would you be
absolutely.
able to zoom in a little?
Okay, is this better?
Yeah, I think that's much better. Thank you.
Okay, yeah. I can maybe do a little more.
Yeah, that's fine. Thanks.
Sorry, it's yeah, I'm not really good with touchpad. Okay. So I do have my cluster ready, and let's just jump right in to the UI. So this will not work. So I need to copy the host name. Obviously, the server itself righteously thinks about it as localhost, but I know that it is indeed running here, my H2O flow. So this is the point and click environment, and I can see already if I just go ahead and click on data and list all frames, I already do have my data set here. So I'll just go back and start the experiment. So let's have a look at how the data is organized. So this is the first 10 rows. So I do have some information. So this data set actually is coming from Freddie Mac, and it contains, I think, 20 years of mortgage data, and it has some demographic features, as you can see, and loan performance KPIs and credit performance dispositions and other credit related figures. What we will be doing is we are going to predict whether or not the holder of the loan will default. So we will be predicting delinquency of this particular loan holder and his or her loan. So let's have a look at the structured data. So you can see we have roughly 500,000 rows, 27 columns, and some of the types you can see. And it is important to have a look at the structure of our target. So we said we would be interested in the delinquency, and it's a binary classification problem. So we will be trying to train a model that would predict whether or not the delinquency happens, and you can see that this is massively so that the data is imbalanced quite a lot towards people who pay well. So to be able to build a machine learning model, we need to take the whole data set and split it. So we will split it into train, validation, and test set. The train set will be used for building the model. The validation set will be used for validating how good the model has been how well the model has been trained, and for optimizing the model further. And the test set, we will just leave that, keep that intact, and we will not touch it for the training purposes. And we will come back to that at the very end to compare the model performance. So you can see the number of items here, and I will also go ahead and create couple of variables. So y is our target, and this will be the delinquent column. We will ignore columns that obviously we can ignore the target, and then we will ignore two columns, one prepaid and payment penalty mortgage flag, which by its values give away the target. So in data science, we call this data leakage, and we will not obviously have a knowledge about the those columns or the values inside of those columns at the prediction time. So it is not possible for us. Well, if we train the model using those columns, it would not be useful in production. And as well, production type is a feature that is the same for all of the observations. So we will also drop it. And this is the set of our columns. Now I will try to show the same thing in H2O flow. So let me go ahead and copy the URL, and you can see. Okay, I will just rid of this. So I can call assist, and I get some basic commands that I can do. So I will be importing files. So I will be importing the file from this location, and I will have a look if it finds it. Yes, it has found it, so I will import the file. So I'm actually doing the same thing that I was doing in the in Python client. So parse this file. Now H2O will just have a look at it, and it will give me some hints on the parser. Will try to guess the types. So these types are fine, and therefore I will click parse to really do the actual parsing and ingestion of the data. And now if this was a large cluster, all the data would be distributed across the cluster. I will click on view and can have a look at the data. I can click on each of the columns. So what we were doing in Python client, I was checking the delinquency. So you can see there's this distribution. It's really highly imbalanced. There's some more statistics. We can do some more data prep things here, but for the sake of time, we will not look at that. So what I want to do here is I want to make sure that I have the same split. So I will call this flow train. And I think we did 70, 15, 15. So flow train, flow valid, and gosh, okay. So bear with my with a lack of talent for the UI that I have. So flow train, this will be flow valid, and this would be flow test. I can, okay, my favorite number, and I have my 3 frames here. Okay, so I think I can go back here and have a look at what we're up to next. Okay, so at this point, at this stage, I will be building a GLM model. So the GLM model, I will first build it through Python, and I will just go ahead and this first row creates the estimator itself. So this does not really train anything just yet. And when I call this second row, I will already train the GLM model, and I will see that it's really fast. And we can have a look at how the model looks. So it's so since it's a binomial, so our task is binomial classification. So I only need to make sure that I say this is a binomial task, and I just name it somehow. And the model that has been built now is showing me some accuracy metrics. It's showing me confusion metrics, showing me the error of first and second type. What is important here is my max F1 metric, and because the data set that I'm using is highly imbalanced. So the F1 score is something that that can measure the goodness of a misclassification. And here here is a table that shows me it shows me the progression. And you just scroll down, and this is the scoring history. So you can see that in that half a second that the model has been building, the score was improving, and I can see how this went on. I will call this GLM plot, and here you can see that in each iteration, in the first iteration, the error was dropping significantly, and then in the further iterations, well, not me, but the model was plateauing and could be ended prematurely. So let's have a look at what the model thinks is important. So this is my variable importance chart, and you can see that the most significant name feature is the servicer name, and the most so how to interpret this? So we have different, well, the clients are using different banks that are called services, and the reason and these four different ones are different banks, and basically the fact how these banks operate with that given customer this affects the overall probability of the delinquency. Let's have a look at the GLM accuracy. This is quite nice, and let's have a look at how we actually can utilize the model itself. So this is just predicting on the first 10 rows of my validation data set, and you can see that that the probability of false and true is being displayed, and the label is being determined by the best F1 score that the GLM model has achieved. I will store the validation score into a variable, and we will use that later. So I will go ahead and try to do the same thing in Flow. So I can do it in several ways. I can do it from the perspective of my frame. So I have created those splits. So I will say, okay, on this train frame, I will build a model. So I will select the GLM model, and here I have a lot of things that I can set up. So I will do something slightly different. I will use cross validation. So I will not select the validation frame, but I would rather select 5 faults. Response column is delinquent, and let me see what were the columns that I was dropping again, so that I do not make a mistake, and this is reproducible. So sorry for the scrolling. So it was prepaid, and the penalty. So they both come up, and then I think it was the product type, right? And the delinquent I don't need to, because it's already in there. So family. So I need to tell that it's a binomial classification. And I think I am good to go. So as you can see, there's a lot of stuff that you can set up, and that's what makes this really powerful for the data scientists. Okay, so I will. I see that this model is now being built, and I can have a look at how the model has scored, and you can see there's a lot of descriptions with the model parameters, scoring history. You kind of see the same thing as in the Python Jupyter notebook. Here's ROC curve, so you can see that it's actually performing quite well. Here are my coefficients. So this is again the importance chart and other metrics. Okay. So let's carry on. I think we will. We need to build the next model a little bit faster. So random forest. So what I would be doing now is pretty much the same thing. I will build a random forest estimator and train it on the same data. Once it is done, we will have a look at how it was doing. So what's that for the sake of clarity? What's the difference between the GLM and random forest, or what is random forest? It's an ensemble technique which is building trees, a certain number of trees that then all of them are all of the predictions of individual trees are being averaged, and the prediction of is then computed by this ensemble. So you can see, I have collapsed that by mistake. You can see that currently we have built 50 trees, and that's the default actually. And there's a number of leaves and not, and the interesting metrics. You can see there's the confusion metrics, so we still tend to have a much higher error in true. So we misclassify the actual delinquency, because that's actually the nature of the imbalance data sets, but it's not too bad. So our F1 score is slightly better, and you can see more of the documentation and variable importance here. Again, the property state is the most, well, not again, this time property state is the most important variable, and so this depends actually on the state of the if someone is trying to buy the property or not. So that's what this variable tells us, and it makes good sense that it's an important one. We can go ahead and plot the AUC for training and validation, and you can see that for the validation it is performing better. So there's a good use of the validation. So it's actually overfits slightly on the validation data set. Here's the validation. So the variable importance plot again, and this is a nice new addition, partial dependency plot. So we will take credit score, and we will see what happens if we keep changing the values of credit score and in the input data set, and how they would impact the overall score. I will just queue up all the other rows here. So this is not really anything special. It's the same thing that we've done we've done before. So I will wait for this for the PDP to appear, and it's here, and it's showing the picture. I think tells it best, and you can see that with the growing credit score, the mean response, that is the delinquency, is actually dropping. So this is sort of a what if analysis that we can perform on any column that we like. Let me go ahead and try to build the random forest quickly in Flow. So again, I'm able to do it differently. I can click on model, and I can click on random forest, distributed random forests, and here I need to select the training and test data set. Again, okay, I don't want to use the validation, so I again will be using cross validation. Response column is delinquent, and I will ignore the columns that I have. Property, product type, and what was that again? So the penalty and prepaid. Okay, and I will go ahead and build a model. Because the time is running, I can just go ahead and train a GBM model. This is really the same thing, different algorithm. It works differently. GBM models tend to be most powerful among the ones that we are trying. The difference is that they optimize the building of next tree in the ensemble to minimize the error in the process. So I can see I get the same kind of information about the GBM that has been built, and I can see the accuracy and so on. So I think this I can come back here, and I can see that the model is still training for the random forest. I will skip training the GBM in Flow, and I will much rather go ahead and explain the grid search that we have. So as said, the machine learning models have a number of parameters that you can set, and some of them may be very crucial. So in this example, this is the simplest of the models, and in this example, we will be changing the values of the alpha, lambda, and the flag how to handle missing values, right? So we will. So the alpha is a distribution of regularization between L1 and L2 penalties, so between lasso and ridge, and the lambda is the strength of regularization. And lastly, obviously, missing value handling, you can skip, impute the mean value, or you can. There are some other tactics, but we will just include these values. You can see that we've used a for loop to generate some some of the values for our grid. We do have two possibilities for the grid search. We have a Cartesian grid search, which just goes through a preset number of values. This is what we're looking at here. And then we have a random grid search. And the random grid search kind of generates randomly the coverage of the search space, and both have different usages. So let me just set up this and run it. And what happens now is that I have search criteria in place, which allow me to say, okay, the maximum number of the models is 200. The maximum runtime is 300 seconds. So that's 5 minutes. And for the sake of reproducibility, I have the seed here. And we are now using the strategy is random discrete. So we will cover the space that we have defined using a random grid search. So once this is done, we will be able to see the leaderboard of different settings and select the best model. I will go ahead and show you how to do the same thing in Flow. So I will go ahead and click on GLM, and I will just do the same thing again that I have done. Let me just use the validation set this time around, and response column. And you can see that there is a column called grid, and there are in certain rows there are checkboxes. So I will just explain. I need to send this to binary. And what we will be doing here is we wanted to optimize the alpha lambda values. So in this case, I would probably say, okay, I want 0.01 and maybe 0.01. Okay, I said it wrong the first time. You can read what I'm typing and, you know, have some representative values, maybe 5, 9, and 0.99. So this would be defining the values that I want to. This is the coverage of the search space. Now I will click on grid. Okay, so I should be doing that the other way around, and I can do that also for lambda, and I could also do that for my empty for my missing value handling. And I would build a model, and the model would be now being built with the grid search, which is exactly what we've achieved here in Python client. So let's have a look at the leaderboard, and then we will see that we will get some. So there are some values of lambda and alpha and missing values handling strategies and the respective AUC score. And there's the ID of your model, and you can go ahead and see the best one, which is the most powerful one, and we can have a look and print some information. So you can see that we have tuned the GLM model and have gotten an uplift in performance. And well, I will skip this, and we have also hopefully gotten some change. And you can see that there's a trade-off, and this is the last thing I'm going to show. So there's a trade-off between tuned GLM overall accuracy and the error rate. So we are pushing towards one or another direction. So in this case, we really have put a hard limit on the amount of trials of how to export the search space, but in reality, you would probably have that thing running for a longer time. In order to keep some time for questions, I will just waive the rest of the presentation by saying by showing that we can do the same thing for random forest, and I don't want to repeat myself too much. So we have different hyperparameters. So we would first try to find out what's the best max depth, and we will find, and we do not want to have it too large so that we do not overfit on train, and we also don't want to have it too small, because then that would not perform. And then further, once we have the this determined, we will try to optimize some other hyperparameters. And I will just tell you that at the end, the story ends up well, and our models that we have that we have built perform better when they are tuned than the untuned bridges, I think, there. So it's a lot to cover with our open source framework, and the amount of content that I have prepared is also quite large. So I would encourage you to go ahead to I think it's training.h2o.ai, and there you can follow what we were looking at, and that's really good explanation, and you can have fun time with H2O open source. So Ivan, how do the questions look, and
Yes.
what do we do now? Do we have enough, or do you want me to carry on?
I think we'll keep some time for questions. So we received a lot of questions, and we won't be able to answer all of them now, but we will make sure to get back to you individually if we didn't answer your question. So Stefan, what would you say is the main competitive advantage of H2O?
So I hope that by now it would be clear, and that is the possibility to build really good models with a lot of freedom for optimization and for setting up a lot of details on very large data sets. So in reality, what we see with our customers is that you don't really have any other choice if you want to train on data sets that are terabytes in size, and you want to use all of the data, do no sampling, and work like that. So you would end up having a large Spark or Hadoop clusters with a lot of memory on them, and this is the primary field where H2O really shines, and there's not really much else on the market.
Okay. Is it possible to participate to this open source project, and how to extend the H2O-3 and open source projects further, and also what would be the areas to extend?
Mm-hmm. Yes. So this is a first-class citizen in the free and open source software world. So we do have all our code online on GitHub. There are pull requests that you can open, and it is absolutely welcome to cooperate on the development. I think it is one of the areas would be maybe adding some new algorithms or some functionality in feature engineering, maybe functionality. Yeah, or the other thing that I can think of it would be utilizing our deliverables in some of the machine learning platforms for deployment. So we do support things like MLflow and others, but this is another good idea for open source development.
Okay. Could you clarify how to deploy H2O-3?
Mm-hmm. It's very, very simple. The simplest of all ways is you download the jar file and you just jar run it, and you have the cluster running. You can do it maybe even more, even in a more easy fashion. So if you recall what we've done at the very beginning of our presentation, we have imported H2O, and we have called H2O in a, and this is all you do. So the Python wheel that you installed would be imported, would do all the trick for you. If you want to use it in more enterprise fashion, we do have a tool called Steam, which you would install on a Hadoop edge node or edge node of a Spark cluster, and you would point and click and get your clusters from a nice looking UI. But that is an enterprise feature, and that is available only for enterprise customers.
Okay, I think now we'll go into more technical questions. So does the platform support cloud and in-memory DB?
So the platform supports cloud. Does the platform support cloud? I can see this as a maybe at least twofold question. For running H2O, yes, absolutely. We even have a homegrown solution that runs that on cloud on EC2 instances, and really anywhere where you can host Java, it runs. That is for the cluster. Then once you train your model, you can download a deployable let me just I have some backup slides here. So you can deploy onto cloud using our Pojo or Mojo, and really that can be utilized anywhere inside of a database as a stored procedure. So we do have Hive UDF functions, for instance, for scoring and so on. We also have some good user stories with embedded devices and so on. So there's a lot of freedom in that.
Okay, thanks. What about running H2O with Docker and Kubernetes in connection with the Jupyter Notebook interface?
Mm-hmm. Yeah, so as I've already mentioned, this platform called Steam. It does have a connector to all kinds of deployments of Kubernetes clusters. So it would be Elastic, EKS on AWS, or your vanilla Kubernetes cluster on premise. We do have a way to really seamlessly deploy the clusters onto that. Then again, for scoring logic, this is super easy. We do have some pre-built Docker images that we can show you how to deploy the scoring engine onto Docker, and therefore you can easily get it running on Kubernetes as well.
Okay, thanks. Is there a limit to the number of parameters that can be introduced to build a model?
So the parameters that the parameters are given, and the values for the grid search is not really limited. The number of values for the grid search. I'm not sure if I follow the question well. Maybe just ask it once again. So the number of parameters are, it's just fixed, right? Like this number of parameters here, you cannot extend. It's just given. Mm-hmm. The number of values, if you want to do a grid search, this is kind of unlimited when it's continuous variable. For categorical variables, obviously the number of categories is your limit.
Okay, thank you. I think we'll take one last question for today, and that is, what is the difference between H2O-3 and our enterprise platform driverless AI?
A very good question. So H2O-3 runs in a distributed fashion, possibly on a large number of even not so powerful nodes or even weak nodes, and is written in Java. It's fully open source, and it is a tool for skilled data scientists. And it gives you a lot of freedom, but you have to work with the tool manually and write code, and it is very powerful, but requires skill. Whereas driverless AI is a platform that automates all kinds of steps for you. So you would just, as a bare minimum, you would just go and select your target variable, tell it how hard it should try, how much time you give it, and how interpretable your model should be. And driverless AI then goes and through the data set, picks the best algorithms for you, picks the best settings, and goes ahead and performs very intensive feature engineering, tries very many feature engineering tricks to really represent your data set. Then on top of that, it creates machine learning interpretability. Well, it uses this functionality to give you a lot of explanations into how the model works, whether it is fair or not. And just by one click of a button, you can deploy your model onto a production deployment site and work with it, monitor it, and automatically rebuild the model when it's starts drifting and so on. So it's more enterprise ready. It automates a lot of stuff. It helps the junior data scientist to perform more senior tasks, or the senior wants to be more effective. But it obviously does not have this level of detailed setup, and it does not scale beyond limits. It runs a single computation is run on one physical node with a lot of GPUs, and you can have a really bulky machine, but the limit is the physical limitation of the machine currently.
Okay, great. Thank you, Stefan, for taking the time today, and thank you to everyone who joined us. The recording of this session will be available on our YouTube channel later today. We hope you enjoyed the presentation. Stay tuned for our next events and have a great day.
Thank you, everybody.